My name is Jose Liste. I am a technical marketing engineer at Cisco, and I've been working a lot with Clarence and the team on segment routing, and they asked me if I could show you a couple of the innovations that Clarence mentioned. We'll do two demonstrations. First, we'll do what we call on-demand next hops, or ODN, and that will also include a demonstration of segment routing PCE server in iOS XR. So this is a demonstration about traffic engineering. So if you present a network device that runs segment routing with a problem, I want to go from 1 to 3, and I want to be able to have a path that does not go through the red link, 2 and 3. The algorithm, whether it is central or distributed, will come back with a label list, says go to 7, that's the blue instruction, 16,007, and then take the link between 7 and 3. That's my second instruction, 2473. That is what I need to impose as a head end on device number 1. That's all the theory. In practical terms, then somebody would have to take care of the SRTE policy, which is what the router algorithm or the controller told me to compute. Now, what do I do with this policy? Do I configure it manually? Or do I let my PCE protocol, for example, instantiate such a policy on the router?
Okay, question. All right, so couldn't you also go to 16007 and then let the default routing handle it from there?
Yeah.
Do you have to have 24073 in there? Or
I could also, so the question is, could I just go to 7 and then tell him go to 3 following IGP? Mm-hmm. So the second instruction would have been the global seed of 3. I could do that. But if you notice, that link between 7 and 3 has a very high metric, high cost. Mm-hmm. So the global routing will take me back. So I'm showing a specific case where I must use an adjacency seed, which is go over this link.
Okay.
If I let the IGP will just will come back, and it will go over the red link, which is not what I want.
Okay.
But if I remove that metric from there, the regular routing will take me through that link, yes. So back to the problem of how do I instantiate the policy on the router? Well, if I have my analogy with TE tunnels, RSVP TE, well, you configure a tunnel, or you let PCE instantiate one. The second one, how do I steer traffic onto these policies? Do I do static route? Do I use auto route announce? Do I use PBTS, PBR? Well, for people who have worked with RSVP TE, they're going to be very comfortable if I tell them that they have to take care of these issues this way. When we started talking with customers, the answer was, or the question was, the challenge was, can you do better? Okay. Can you do better than before? Can you create these SRTE policies on demand towards a VPN next hop? So imagine you have an L3 VPN route coming in onto a PE that has a BGP next hop, which is the advertiser of the prefix. Can you build and instantiate a policy on demand towards that VPN next hop? I do not want to manually configure the policies. I do not even want my service orchestrator, in Cisco terms will be tail-left NSO, to deal with transport objects. I only want my service orchestrator to deal with service, not with transport. I don't even want my controller, my PCE controller, instantiating anything on my router. I want the controller to compute, not to instantiate. That is the first challenge. The second challenge, can you automatically steer VPN traffic onto the policies? I do not want to use static routes. I do not want PBR. I don't want PBTS. I don't want to use auto route announce. Some of these features will have even a performance penalty that I don't want to incur. So the answer to these two questions, which I hopefully will get you interested in the remaining of the demo, is yes, we can do this with ODN. Short for on-demand next hop. Okay. So today in this demo, we're going to cover the two principles of ODN. We're going to trigger policies automatically so that you don't have to configure them. We're going to trigger automatic steering onto the policies as well. Okay. And the use case that we're going to show you is a high-scale multi-domain network where there is no connectivity between the endpoints. So the head end cannot compute a policy to get to the destination. So he needs to go up and ask a controller for the computation. We're going to be asking a segment routing stateful PCE server, give me a transport LSP to my tail end, which is my BPN next hop. Okay? And we're going to use a segment routing PCE server which resides inside of an iOS XR router. It's a feature on a router. So the controller is now a device that looks like a route reflector position in the network. He's learning the topology, and now he's ready to compute for you. So here's the topology of the demonstration. I have two domains, domain 1, domain 2. They happen to be running ISIS as an IGP, and they're enabled for MPLS segment routing. At the edges, I have a customer or a tenant, which is going to be getting services through L3 VPN. So I have a hypothetical VRF blue. Loopbacks, which are going to be my anchor points for BGP, also are going to have the global MPLS or prefix seed for segment routing. So the loopback 1.1.3 has the prefix seed 16003. And if you look at the rest, you will find that every loopback has a global prefix seed.
So how are those IDs assigned?
So the question was, how are these prefix seeds assigned? At the moment that you configure the loopback, you also assign the prefix seed. So it is on the operator to assign them. One way is to make sure that they actually make sense for whatever he or she wants, so they're actually locally configured and that they're assigned by the operator.
Are there tools to make sure that you don't have overlap? Because having two machines with the same ID is probably not a real good idea.
The principal rule is that two prefixes share the same prefix seed. They cannot. So if 1.1.3 has 16003, no other device should have 16003.
Correct. So what tools exist to make sure that that's unique?
So what you do is you have instrumentation.
My point is this getting us back to a spreadsheet again for managing these?
No, so what will happen is this. Anytime you have a conflict, then you're going to have instrumentation from the routers telling you, hey, I see a conflict.
Okay.
So you will start getting alarms. There are also drafts which are progressing in the Spring Working Group on what are the algorithms and how do you want different implementations to react whenever they see a conflict.
Okay, very good.
Beyond instrumentation. Yes, question.
So just to be specific, if I configure router 3 and router 7 and I typo that, they both have the same SID, it's going to throw a syslog, something, right?
Yeah,
or a trap.
What's going to happen is routers are propagating this prefix to level mapping via ISIS LSAs or OSPF LSAs. Mm-hmm. So people will start complaining because 13, 5, 9, even 7, they will see each other's conflict through the LSAs.
So the routers will start chattering in logs. Yes. Okay, that's what I'm getting at. Is am I going to see this in like
you will see it.
My Oak stack?
Yeah, you will see it.
But by then you've already done it. And you've already.
Well, yeah, but I mean, it's better to have it fail and be chatty than fail and be silent.
Exactly.
Now, that's not to say that there is another concept which I think people mentioned was the Anycast seed. You could have two routers advertising the same prefix, prefix seed. So 3 and 7 could have a secondary loopback 100 for 1.1.1.100, and they both advertise 16100. So that's valid in the architecture, and that's heavily thought of, looked for by operators. Okay.
How are we sharing labels between the ASs, or is that not a thing?
Ah, very good. So my last click, I do nothing. In this case, I'm taking it to the extreme. I have an operator that is growing at such a rate that he wants to separate IGP domains completely. And he wants, per design, to redistribute nothing between the domains. So if I have PE number 3, he has no IGP knowledge on how to get to 22. Absolutely nothing. And that's why we're working with some customers who want to get to this model. So I mentioned a segment routing PCE. Well, we use Path Computation Element Protocol to establish communication between the edge devices, the PEs, 3, 7, 22, 23, and the PCE server. The PCE server, as I mentioned earlier, is router number 10, is an iOS XR router, acting as a segment routing PCE. All the edge devices are clients. So I have my PCEP sessions in the order shown in the arrows. Okay? Between 3 and 10, 7 and 10. Some people get worried. If I show this picture, oh, wait a moment. Are you saying that I have a God box? I have 10. If 10 goes away, then I have no brain. Well, of course, you can configure multiple PCE servers in your network. So this is just for simplification. Service-wise, how am I going to be learning my service routes? I have my L3 VPN route reflectors, so that's business as usual. So I have my multi-protocol BGP between 3, 7, and the other PEs up to the route reflector. The last element, how does the controller learn the topology? So Paul, Mark, and others mentioned this. So I'm going to use BGPLS so that my controller number 10 is getting the entire topology from both domains via BGPLS. In this case, I chose to feed it from the interdomain router number 5 and number 9, which know both domains to the left and to the right. All right, promise, this is my last slide before going to the demo. The sequence begins like this. I have a customer CE21 that is advertising a prefix route 2.2.2.21. This is in the context of BRF Blue. The operator knows that this customer has purchased low latency service on that VPN. So now what the far end PE22 will do is he will tag that advertisement with a regular BGP extended community, let's say 100:777. Okay. The route will progress in the operator network through the route reflector 11. It gets to 3. Now 3 has a hint. 3 is getting a VPN route with a very special community that says, I need low latency path to get to that prefix. And right here is where we start the demo. Okay? I'm going to take you to the topology, and we're going to gravitate on 3 and 10, the server, the PC server, and the local PE3.
Sorry, I think I missed it, but how does PE22 know that it should get low latency?
Oh, well, no. So there's actually policy configured on 22. Let's say you have a route policy in BGP. You know, 22 knows, well, the customer knows about that special tenant that needs low latency. So there is actually configured knowledge on 22 that says, if I receive this prefix, or if I get any prefix from that CE, I need to tag it with this community.
Oh, so that's statically defined on 22.
Yeah. 22 is in charge of marking the route. That's all it's doing.
So it's, okay, but it's giving it a community. It's not,
yeah.
That's all it's doing. It's just,
It's only a hint.
okay.
So 22 is doing nothing special for what you're going to see. 22 is just marking BGP routes.
So that community then is defined on the PCE or some other box to say, okay, this is low latency.
It's actually defined on 3. On 3, I have a recipe that says, if I see that community, we got to behave differently. And that's on 3. I'll show you.
So like other standard BGP communities, that needs to be consistent across all the mesh, right? So every intermediate node will need to know what that community means as well.
Well, you
just
could,
like typical.
Yeah, typical behavior. We have not introduced anything new onto onto the community itself. It's just that it has a meaning. It has a special meaning when it gets to 3.
Just to be clear about
Yes, indeed. So there is nothing special about that community from a BGP point of view. It's just another community.
Right.
So we're going to go to the routers here in a moment. 3, let me go to 10. Let me go to 21. Is this large enough for you to read? It is? Okay. So then we'll stay this way then. Let me close these guys. Get my cheat sheet so I don't forget what I want to show you. I'm going to go, so reminder then. So we're going to go back to the topology. That's the same topology that I showed you earlier. So we're going to go to device number 3, and then we're going to go to device number 10. So device number 3 has has a BGP neighbor with a route reflector 11. So right here, 11, where he's getting the routes. And now he has an RPL, route policy in iOS XR, if you're not familiar, where I'm just going to be matching on the community. In this case, it happened to be 100,777. I have another community as well, but that's the primary role. Let's have a look at that route policy. The route policy is just matching on the community. In this case, these are variables, A, B. I just match on it. And what I'm going to do is I'm going to set a recipe, or we call it a TE attribute set called gold. Gold is what you were asking me. Once I recognize that I have a route that is marked with that color, gold will tell me what to do. I want to show you what gold looks like. So this is the definition of gold. It's a recipe. And the definition says we got to talk to the server, to the PCE. So the gold recipe says you got to talk to the PCE server. I'm going to skip this line for a moment, but it's very powerful. And then you're going to request a path that it optimizes for TE metric. Now, path to whom? A path to the VPN BGP next hop. Okay. But that is not defined in the policy itself. In the policy itself, you define who do you talk to and what constraints you want to ask. One of the constraints that are very appealing to customers, you can ask for disjointness. So you can request disjointness from another LSP in the network. Now, start thinking about this. You're talking about LSPs which have a different head end than 3. So now I'm requesting, I have 2 LSPs in the network, different head ends. Of course, device 3 has no clue where that LSP is going, so it's going to the central element, says, keep me disjoint from that LSP that it is in a particular group ID 1. Now, who is the PCE? So if we take a look at the configuration, different. Here are my PCE servers. So I have a device 1.1.10 and 1.1.12, different precedents. I have multiple PCE servers. That is the controller, the device number 10, and 12, which is not shown. Okay. So let's go to the controller. One of the principles from Mark early on in his topic about the simplicity. This is a regular iOS XR router. And what this router has, it basically has the algorithms that have been defined for segment routing SRTE, packed in an iOS XR image. This is the configuration of your controller. So you go to the controller and you tell him, this is you are a server, and that's the IP address that I want you to listen on, and that's it. That's your PCE server. Now, the algorithms are inside the XR image. The request will come in, and then he will honor the request if he can. How is the controller learning the topology? So this router number 10 basically is going to have a BGP session with 5 and with 9 for link state BGPLS. And here we see it. I have sessions with 5 and 9 where the only thing I do is just enable BGPLS. There is no other address family. Now, the updates will come in. I think I have an alias here, BGP all. Yeah. So in fact, I have a session with 5 that has 82 prefixes that describe the entire network. These are LS prefixes. Okay. Now, all of this fits into the PCE topology database, and now I can request the router, tell me what do you know about one device in particular. I'm going to be asking him, I'm on 10, describe to me what you learned about 3. And 3 has basically 1, 2, 3 MPLS interfaces and 1 facing the CE that I don't need to describe. So if I execute, by the way, these are all iOS XR aliases, so this is not a particular new command that you have to learn. So I'm saying, give me the topology that you have learned via LS for 1.1.1.3, which is that box number 3. And now here we have already implemented extensions to BGPLS such that the segment routing labels are advertised in BGPLS. So I know the prefix SID, I know the loopback 1.1.3 and the seed 16,003, if you remember. I'm learning now that there are 3 links, link 0, link 1, and link 2. These are the 3 links on that device number 3, 3 to 7, 3 to 13, 3 to 5. They have all been described to the controller. If you remember the theory, every link will have 2 adjacency seeds, one for protection and one without protection. So for every link, I have learned 2 adjacency seeds each. So I have 6 of them total for this box. If you imagine the controller knows this about everybody else, so now he's ready to take on requests. So I'm going to come back to 3, and I'm going to do an alias that tells me, show me if you have any policies. In this case, show me if you have any tunnels. So when I run the command, there is nothing. So it's empty. What I'm going to do is I'm going to go to router 21. Remember the loopback that he's advertising? I'm going to unshot the loopback on the CE. And basically then that loopback will be sent over a BGP session to the PE, and then the route will be marked, and then it will arrive on 3, and the magic continues for ODN. So let's go to 21. This is the CE. I have a loopback 2 that is in shutdown state. This is the CE prefix. Okay. I'm going to unshot it. Yes?
At this point, you can't even, so you're going to get that BGP route, but you can't resolve that next one. Because we haven't reached the security.
You need to repeat that.
Yes, so the question is, once you get that BGP route, you're going to have an next hop that you cannot resolve. So will BGP be happy?
Yeah.
Yeah. So right now, I made BGP be happy, and I'll show you how. But now, the way how I made him happy is not how we're going to ship it out. But here, I'm running the earlier prototype. But you are correct, Tim. OK, so I'm going to do a no shot, right? And we're going to commit that. So now the route is now making it all the way to PE3, or at least it should be. Now when I run the same alias, TEB, I have a tunnel. So now I have a tunnel between device 3 and destination 22, 1.1.1.22. Who is 1.1.1.22? It's basically the loopback of the PE that advertised that route. Okay. To prove the point that I was just chatting now with Tim, I have no reachability to 22 via ISIS. So my show ISIS IPv4 route shows I don't have any knowledge how to get there, which is the premise of the design. I do not want to redistribute. Let's take a closer look at that tunnel 5. I want to show you what's inside. So I'm doing a tunnel detail. I have my destination. This is a segment routing tunnel. It is dynamic, computed by PCE, and it has 3 segments. In this prototype, I'm using adjacency seeds to build the path. But the algorithm on the server can compute path actually that minimize the use of adjacency seeds, so that my label stack is actually smaller. If you follow me here with the nomenclature, the IP addressing will tell you where we're going. I'm going from 3 to 5, 5 to 14, 14 to 22. If you follow the drawing, 3 to 5, 5 to 14, 14 to 22. That's the path that was computed by the controller. The link between 5 and 22 is purposely down, so you can see a path that is non-trivial. Okay? So I have an SRTE policy. It was computed by the controller. It was given back to me, and it includes three MPLS labels that I'm going to push. Why 3 and not fewer is because I'm using in this demo adjacency seeds. So I'm using 1 label for each link that I'm traversing.
If you weren't doing that, would it just be whatever the
prefix seeds?
It would be 5 and then 22?
Yes.
Okay.
Go to 5 because you know how, and then go to 22.
Yeah.
Okay. Now, I think it's very important, I think Mark mentioned it, is the binding seed. That policy has an MPLS label, which is local instruction, that says, if anybody is coming onto this device 3 with that label in its pocket, it's going to get onto this policy. And that is the binding seed. It's a very important instruction. It has a value that was determined by the PE 24006. Let's actually explore that label in detail. If I look at my LFIB for 24006, so show MPLS forwarding label 24006, that label is programmed as a POP, which means that I'm never going to put it on the packet going out, and it's pointing to the outgoing interface, which is the policy itself. Now you could start to say, oh, wait a moment. This binding seed is going to be the one that I'm going to use for steering. Because instead of recursing to a BGP next hop in Ceph and in the LFIB, I'm going to be recursing to the binding seed. But let's first take a look at BGP. I'm going to look at the BGP route. So this is the VPN route. So show BGP for the BRF blue and the loopback that we are exploring. Okay. So I'm going to learn my MP multi-protocol BGP label. That's 24005. That's coming from the VPN advertisement. But notice how you can see how BGP knows about the recipe, gold. You see how the route came in with a special community, 10777. And you see how here the TE module in the router gave the key to the card to BGP. So the binding seed is the key to the car that gets me onto the policy. BGP as a client has received the key to the car. 24006, if you remember, that's the binding seed of the policy. Yeah. So now you could have a VPN where you could actually give different treatment to different prefixes in the same VPN. Some prefixes are low latency, some are not. I can go very granular now. I think the biggest point for me is to show how the forwarding is done. So I'm going to look at the Ceph, the IP to MPLS path. So I'm going to do a show Ceph for the VPN prefix 2.2.2.21. We have a new instruction in the FIB that says recursion via label. And then the next hop is the binding seed of the policy. So your next hop is automatically tunnel 5. I did not have to configure auto route, static route, PBR, PBTS. And that's how I do steering. So now I want to prove that I'm able to put traffic onto that policy. So I'm going to go to the CE in the far end, CE2, for which I don't have a connection. I'm going to connect now. Close this. This is the CE on the far end, so we are right here to the left of the picture. And I'm going to do a trace. So I'm tracing 2.2.2.21, which is the far end, and I'm sourcing it from another loopback. And here I can see that if I put this picture a little bit below, I go to 3. From 3, I go to 5. From 5, I go to 14. 14, I go to 22. 22, go to 21. So I'm showing an end-to-end trace from the CE. When the packets get on 3, they automatically get put onto the policy of tunnel 5. And the policy of tunnel 5 is going over the path that the controller told me to use. And that is basically wrapping up the demonstration of how a router can intelligently make a decision when he doesn't have connectivity, or because he's told, he can go to another entity and get a path for an otherwise unreachable prefix. And the programming of the resulting path into the data plane so that incoming traffic get automatically put onto that policy. Yes?
Can you talk about the significance of the MPLS labels in that trace route there?
Yes, of course I can. So here, if we take a look, these first two, remember my path had 3 segments. Okay? So if I put the picture here for you, I got a segment that took me from 3 to 5, 5 to 14, 14 to 22. Here you see 3 labels. The bottommost label is the BPN label, 24,005. And the remaining 2 are the labels that take me from 5 to 14 and 14 to 22. How come I don't see the label from 3 to 5? Because it's local. I knew the way to get out, so the label between 3 and 5 never gets programmed onto the packet. And that's the answer. Now, all right, so to finish up, let's actually go back to the far end CE. I'm going to do a rollback. So I'm going to shut down that loopback again. So the loopback is going to be shut down. If I go back to the CE, I do my trace, my trace fails. So the BGP route was withdrawn. Ceph is no longer programmed. I don't pass traffic anymore over that path. The path actually, eventually, is going to be removed. If I go to 3, you probably will not. Well, if I go to Ceph, you will see that the Ceph entry is no longer programmed. If I go to the tunnel database, there is no tunnel. That's our first demo, ODN and segment routing PCE in iOS XR. Any comments, questions?
I think it's nice to see sort of, and you touched on it when I asked, that the labels are globally significant and the ones that are local are not in that path. So, you know, anyone who's ever done troubleshooting on an MPLS network knows that the tracing back the labels is painful.
Right.
And so now we have this list of globally known labels within the troubleshooting process that we can just go, okay, I know what that is. And in theory, all that stuff's documented, or it's in a DNS text record or something like, you know, makes it a little fine.
And in this example, you didn't see a path that was using global labels because I'm showing you the adjacency prototype. But indeed, yes, you're correct. You will have a path that is only using prefix seeds or as much as possible. And these prefix seeds will make sense to somebody once you see them. And actually, Mark was alluding to this fact. Mark was alluding to this fact earlier, saying that somehow these global labels make it people click. And now because they really have end-to-end meaning. Yeah.
So what ultimately resolves in BGP route is the boundaries.
So ultimately, BGP as a client requested a path to TE. TE got the path from the controller, and now TE gave back the binding seed to BGP.
And it recurses over that binding seed
Yes.
to expand it to the label stack.
So I'm sorry, I should repeat the question. So yes, BGP was the client. He had a BGP next hop that he was told to talk to TE. TE contacted the PC, got a path back, and then TE gave the binding seed to the client, which is BGP. Is this whole concept only limited to VPN routes? What about L2 VPN if I have pseudo wires? It also pertains to L2 VPN. It's not restricted to L3 only. So, okay. Any other comment or question?
If you did it like an XConnect, targeted LDP, is that going to work, or is this just for like VPLS?
Yeah. So here we're not showing you the I'm not showing you the solution for L2 VPN. We're working through the details right now. But the idea is that you should be able to signal the pseudo wires in the regular way.
Okay.
But now you're going to be able to steer the pseudo wire traffic onto a LSP that meets the requirements of that pseudo wire.